Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Camera Tuesday, we're going to talk about audio, bit depth and sample size. So let's dive deep into it. So you have to understand audio itself first. Well, it's a analog data. What does that mean? That simply means there is no break in the signal. The signal comes in and goes in, meaning no matter how much you slice in, it will always be there. And it's a two-dimensional data vector. What does that mean? That means you need two control factors to monitor it, map it properly and recreate it properly. So first is time, basically how many times a second. Second is amplitude, how loud or how quiet it is. So these are the two vectors that you have to control in order to digitize analog signal into a digital domain. Now, real world signal flat out, like a real person, like just talking, has infinite resolution, meaning it's limited by your technological limitation, not by the physical thing there. Like it can just keep going in. Basically, how we have infinite resolution in real world. Like let's say you take a photo of a rock, you can keep zooming in, you can go into microscope and you can go to electron microscope, you can keep going in. So it's same thing with audio. You can keep going down, keep subdividing, but at some point you will run out of basically everything else. Then you will be like, are you actually digitizing or you're just filling up hard drives? So fundamentally, there has to be a point where you have to stop, where it's like, dude, I think we have captured enough. And then you're like, we good. This is a fundamental requirement of digitization. Every analog to digital converter, this is their fundamental core. Like how far do you go and when do you stop? Because you have to understand, you cannot ever replicate 100% true signature of it, because again, infinite resolution is there. You can reach a point where it's close enough, where it's like, dude, more than good enough. An analog medium, as in like tape reels, they were surprisingly good. Like they were analog, but they were surprisingly good at capturing analog feel. For example, if you remember good old days of basically tape to tape reels, these tape to tape reels always had this setting where they can increase the speed or decrease the tape speed. Why? That's what they were doing. They were controlling the time factor, basically how many samples are being recorded, not digitally samples, as in like how long they are giving a ribbon basically to go above the playhead. So faster it was, the basically shorter time slice they were getting and much higher resolution. Amplitude, again, amplitude actually went through an analog circuit, converted into actual electromagnet. So coupling was very good. So we as a human species was surprisingly good at audio. Like as early as like 1920s and 30s, we got audio. Like we got it sorted now. Like, wait a minute, then why don't we have good audio from back then? Well, recording audio was good. Making masters, good. HD. This was the limitation of analog medium. Till that point, basically, if person is recording, it's getting recorded, audio is top quality, like almost as good as modern recording system. It's good. Now, what's the problem? This, let's say it has to be mastered. So it will be cloned 10 times. The moment you did that 10 times cloning, it already reduced somewhat of fidelity. Then you're gonna send all these basically tape to tape reels into cassette player manufacturing, and then they're gonna keep replicating it. Every replication is gonna happen from master, and master will degrade over time. So while they were awesome at capturing audio, they were not very awesome at retaining it. And be mindful, they were magnetic, so Earth's magnetic field over time was also causing havoc on them. So digital took quite some time to reach here. Basically, we figured out the logic of it, mathematics of it, but to get the true feel of audio, it took surprisingly long. And that's why you still see people are paying money for basically vinyls, because it has the feel. And we were really good. Like if you have a well-tuned tape to tape rail, well-tuned vinyl disc and all that, just you'll be shocked how high resolution it is. Like really shocked. We figured out audio surprisingly early. Like digital took time, but analog audio was like, we good. So let's understand some mathematics here. Now, mathematics is his deal. You want to capture as much as you can, but what's the limiting factor of you? As in, like, who's the recipient? We are not making videos for basically doggies to watch. Like, we do that, but we are not getting feedback from them. They are not telling us, hey, I think this high pitch is not working. So we are limited by this puppy, this ear. So this ear has limited resolution in both factor, in time and in amplitude. Basically, how high of a frequency it can handle. It's not that high. And in terms of amplitude is surprisingly good. Like, it's good. Amplitude is good. So time and frequency both are limited. So they are given as a range. So at bare minimum, in perfect anechoic chamber, a perfectly healthy human could discern sound as low frequency as 12 hertz. Generally, most people fail to do that. That's why like its starting point is around 20 hertz, and they can go as high as like Twitter kind of volume of 20 kilohertz or 28 kilohertz. Doggies can go easily more into like 30 or 40 kilohertz. So that's why we call those ultrasound. So this is the time frequency of it. So you take a time and you slice it, basically how many times waves can go up and down. If waves go up and down lower than this, that becomes infrasound, we cannot hear it. If wave becomes higher than that, it becomes ultrasound, we still cannot hear it. So that's the time, basically how quickly it, a pressure wave can change and we can still register it. Then we come to amplitude. Now, time wise, it's not that amazing. Like you start with hertz and then you go to kilohertz. That's a big range, but not that amazing in terms of bandwidth. In terms of amplitude, our amplitude is bonkers. It's like flat out bonkers. The amount of audio levels that we can discern, it's whoa. Like it's so whoa that we cannot even use normal mathematics. We cannot go linear. We have to go logarithmic to it. And be mindful, there is logarithmic of almost everything. You can have log 2, log 3, log 4. We have to use log 10 to properly get that. Like if you remember playing with scientific calculator, it has a log 10 system for that. Like that's how mind-bogglingly sensitive these puppies are. Now, why they are this sensitive? Well, not only they have multiple hairs, that each hair is tuned to receive one frequency resonator, that one frequency create electrical impulses for our brain to discern. There is a membrane, and that membrane has algorithm to tighten it or loosen it. Basically, there is a bone that is like tightening and loosening. There is muscles there. There is actual muscles. And that means our ears have what we call auto gain, meaning imagine this way. Let's say you and your friend, they are sitting in a cafe and you're talking, but the background music slowly over time starts to rise up. Let's say you guys are talking, you started to do that in like late afternoon, but then evening rush started happening. Like background audio level will keep going up. But here's the deal. Both of you would not have noticed that both of you are now talking loudly and you're still able to hear each other. Why? Because your ears automatically figured it out. Your ears were like, okay, now we have to decrease the gain. You decrease the gain, your brain figured it out. Okay, I think that person also have to do that. So let's increase the volume. Like you would not even notice. You will only pay attention to that unless like you randomly get out of those and whoa, it's kind of loud here. It's like, but you were still there. Because our ears have auto gain. That's why like we do not get deaf in basically Daft Punks and all that. Our ears can go very high. Now, we have to create a logarithmic scale and base of 10. Now, the most odd part is we do not have same perception in all the frequency, meaning when we make microphones, you must have heard this, people are talking about, like it has to have flat response. What does that flat response mean? Meaning, if there is 60 decibels of sound pressure at certain frequency, it should capture it. Now, if that 60 decibels, we are creating some sort of sine tone, it should be able to capture flat 60 decibel from like basically 2 hertz to 20 kilohertz, of course. 2 hertz is a bit low, but you get the point. Like it has to be as flat as possible. Our ear is not flat. And not to mention, it's also a compound variable, meaning if you are talking about 130 decibel, our ear will behave completely differently. If you are talking about 120 decibel, our ear behaves completely differently. You're talking about 100 decibel, it behaves completely differently. So there is a curvature based on not only the sound pressure, but our wave frequency. Now, our frequency is designed very specifically for human voice. So we are very sensitive at that, meaning you need very low amplitude, as in like as low as 10 decibel, and you can still hear someone clearly, whereas like I got you, fam. Now when you're talking about like, if you ever wondered why Twitter needs such a small power to work while your subwoofer needs ginormous amount of power, well, some amount of it comes down to physics, but there is another factor into that. Our ears are disproportionately sensitive to high frequency, meaning you look at the high frequency, how in terms of decibel scale, how quickly we can hear it. It's very quickly, you can hear it. Like if you have 5 watts of Twitter power, it will be loud to you. If you have 5 watts of subwoofer power, basically in this end, you can see like it does not even start at like 70 decibel. Like you need very high oomph in order to feel it. Even though if you had a flat microphone there, it will be like, dude, it's subwoofer is already too loud, because it will compensate for this. So you can see that our hearing starts on there, and in the speech center where like most of our brain power goes, we have a lot of hairs that is fine-tuned for that, lot of analog processing algorithm in these puppies, brain puppies, and that's how we listen to it. Everything surrounding it is the zone where you want your music to be, unless you are Daft Punk and all that jazz. Then you push it to almost 10 kilohertz or 20 kilohertz. Or like if you want boom boom, then you go down as low as possible. Generally, you should not go below 15 hertz, but many times people have tried to go to 12 hertz. But at that point, it's like it's only few people be able to actually hear it, rather like it reaches a point where you start to feel it. So people may like it, and be mindful, you have to be very loud decibel, so it actually starts to become shockwave. So this is the whole aspect of it, and be mindful, the upper decibels, it sounds like it's just a decibel. It's not decibel, is you are reaching shockwave territory, meaning threshold of pain is like anything above 120 decibel is starting to harm you. as in like it is harming you, hopefully your body will recover. Anything 130 to 140, yeah, you are in danger. Anything above 140, you're dead. It's reaching shockwave level territory, as in like you have to be at rocket launch to experience that kind of. So I'm pretty sure if you are that close to rocket launch, you're gonna be poofed. So this is a very critical aspect. Our ears have very different behavior, and this is a very important tool for digitization. Whenever you digitize it, there will be noise. So what people do, a very clever thing, they move the noise from hearing speech part, they move it into high frequency. And even though the amplitude is there, like it, let's say noise is 40 decibel noise, you will not feel 40 decibel noise simply because it's in the phase where your ears are not sensitive. That's why some sort of noise our ears can just automatically just tune it out, others it cannot. If it's not able to tune it out, there's a very good chance it's in the speech range. In the speech range, your ears are most sensitive. So anything that's happening here, you're gonna feel the pain. So you wanna make sure it's everything is here or here, only then you can forget about it. So that's the math. It's surprisingly complex. And meanwhile, this is completely different in every person, every individual, every age range. Basically, prepubescent children have different audio hearing system. Teenagers have completely different hearing system. Old men have completely different system. Women also have completely different audio system. These things are just average. So that's the math side of it. It's super complex. Then we come to the time part. So let's understand the sampling side. Now sampling, some very smart people came together and they created Nyquist-Shannon sampling theorem. So what is this Nyquist-Shannon sampling theorem? The idea is they figured out what is the bare minimum that we need. Bare minimum that we need in order to build a what we call analog to digital converter that can give us basically almost perfect representation, almost perfect representation. So what is this mathematics? This mathematics is very simple. Sample rate must be 2x of what you are trying to measure. So basically if you are trying to measure 20 kilohertz, your sampling must be at 40 kilohertz. That's the whole point. Now, there is a very critical caveat into it. The caveat is there must be band limit assumed. For example, if you are talking about human hearing, the microphone that you're using must only start at, let's say, 20 hertz, must dead stop at basically 20 kilohertz. There should not be a time, especially in high frequency, it should not go even 1 hertz out of that. It has to be like dead sure. Now, if you know anything about your audio, you must have noticed we generally don't use 40 kilohertz. We always use 44.1 kilohertz. So why the heck we need 44.1 kilohertz for a 20 kilohertz signal? There lies the main crux of the situation. The band limit that is assumed is never achieved. Like you cannot design a microphone that's like 20 kilohertz, 21 kilohertz signal is like, nope, it drops it. That does not happen. In analog world, that's almost impossible to do. So this 4.1 kilohertz of extra bandwidth is just what we call fall off band. Basically, your microphone and your amplifier, the whole circuit chain has that enough room, that 4 kilohertz room where it's supposed to drop off. The signal drop off should happen. Now, of course, this was after a lot of calculation, lot of deliberation. If your audio amplifier and like a whole pipeline from microphone to or digitizer, it's not dropping off all the signals between this range, yeah, you messed up. So this was as a headroom, buffer room, where it's like you must drop the signal. Once you drop it, once the signal after this point, as in like after let's say 23 or 22 kilohertz, if it's there should not be anything after 22 kilohertz. You have to have a dead stop. It's like nothing goes above basically 4 kilohertz or 22 kilohertz. Once you reach that point, you're good. This theorem will work perfectly. Now be mindful, this theorem has to be applied in reverse also. Meaning when you are going from A to D to DAC, digital to audio analog converter, this filter also has to be applied. Only then you can get a perfect input and output match, meaning the signal that went in is the exact signal that you're going to get out of it. So that's how we do it. So this is how we started, 44.1 kilohertz. Now be mindful, if you have ever used old analog mobile phone or even like let's say 3G mobile phone, you talk to a person and let's say you talk over Wi-Fi or like let's say Bluetooth, not Bluetooth as in like WhatsApp, you must have noticed WhatsApp sound much more fuller. Why the heck is that? Is because this sampling rate is much smaller in your mobile phone and in landline. Why is that? Well, they realized, especially in landline, mobile phone, it was more of a cost cutting measure, but in landline there were physical limit. They did not want to transmit the whole bandwidth of human hearing. They were like, dude, speech is here, so how about we give a little bit of buffer here and there, and that's it. So that's why whenever you're talking about someone in phone, you can hear it, you can understand, but you always know it's something is off. You know something's like it's not feeling full. And when you have HUD calling in mobile phones nowadays, that's what they're doing. They're giving you the whole slicing, 44.1 kilohertz. That whole signal is being transferred. Of course, it's being compressed and all that jazz, but it has enough input that output actually sounds fuller. And be mindful when you are talking speech, the same theorem applies. So if you are really slicing only this bandwidth, you can create a calculation where it's like, okay, you only need, let's say, 5 kilohertz, and you can do that. You can have a full telephonic conversation at that little of a hertz, but be mindful, it will sound very limited, so to say. It will like there's like dead air. It will feel dead left and right, so to say. So it works. It's a very known system. It does work. Now, this is how we started. This is how CD started. CD was the first time where consumer got access to digital audio system, and because of mass production of CD, it became a standard. So standard was 44.1 kilohertz. Over time, we realized it was like not good enough, as in like it was not matching perfectly to our digital video world. So we created a new standard that is 48 kilohertz. Now this sample is generally preferred for video. So if you are recording, let's say, on cameras and all that jazz, generally camera will prefer to record on 48 kilohertz. So slicing and attaching frame rates generally makes more sense. That's 48 kilohertz. Now be mindful, this is just the time variable. You have two axes. One axis is time and you are slicing it. So 44.1 is bare minimum. And can you hear difference above 44.1? Not really. Be mindful, this is time tested. We got this, we know this. You won't hear it. However, you can go much higher than that. You can go 48, of course, for video. It makes a technical sense. What about 88.2 kilohertz? That has 88 samples. What about 96 kilohertz? That has 96,000 samples. What about 192? That has 192,000 samples. Yes, these things makes perfect sense for digital recording. Basically, think of them as raw file capture of the audio in time vector. Be mindful, there are two vectors, time and amplitude. In time amplitude, it's giving time vector, it's giving you more slices. Now, does that matter? Yes, for recording, VFX, these sort of thing, they will do that. Now, would this be helpful to person to hear it? No. This is not even meant for that. What this is meant for, you capture as much as you can and then you apply as much effects you can. And because it has so much sampling, the mathematical algorithms work more efficiently. There are many professionals who can flat out tell you whether this audio stream, especially in Daft Punks and all that, that has like a really lot of what you call digital processing. They can easily tell you, hey, this was mastered in 48 or this was mastered in 192. It makes a difference. So that is the reason why professional audio recording equipment goes to this level. It's not for human hearing. It's more for sound effects recording and actually having enough oomph in the data where when you are applying mathematical algorithms to it, it does not break. So that's why be mindful. For hearing, 44.1, good. 48, comfortable. 88 for mastering, for capturing sound, capturing raw basically. For 92, 192 is like you sorted. But this is only for computer, not for you. So do not just, oh, people can't hear it. It's not for people, it's for algorithms that are processing it. So this is the time vector. Then we come to the amplitude vector. Now, amplitude is a bit more brutal because be mindful, the range is bonkers. It cannot even be shown in basically what we call linear scale. So we use log 10. What does that mean? Every step has a 10x multiplier. Basically, 10 is 10, 20 is 2 zeros, 30 is 3 zeros, 40 is 4 zeros, 50 is 5 zeros, 60 is 6 zeros. That's what log 10 means. It's like bonkers range, you can see. So we have to quantize the data. Now, what does quantization mean? Quantization means whenever you have a sine wave, let's say whatever wave you have, you can keep slicing it as much as you want. Now you're slicing in 2 dimensions, right? Your grid is time and this time is bit. So you zoom in the bit depth, you will find the signal will be close to top or close to bottom, right? Like a bit is a complete slot, it's a line where it's like here, here, here is a complete line. So it will be either go up or go down. That's what we call quantization. It's almost like latching. You are latching the signal. Hey, I think you are closer to the lower part. Okay, you latch to bottom. Okay, your signal is samples is like I think you should go up, down. That's how it's done. So that's what we classify as quantization. Now quantization needs a container. Where the heck you want to store it? That's what we call bit depth. So resolution of amplitude vector, not time. Time we have already sorted. Time is the sample. So resolution of amplitude, this number basically going from 10 to way too many zeros, 10 zeros basically, that has to be stored dynamically, digitally, and that's where we introduce bits. So basically resolution, how quiet your quiet audio can get and how loud your loud audio can get while still retaining enough signature, whereas loud is just not like bah, it's like actually have feelings to it. So for that you need very high bit depth. dynamic range of 16-bit is more than enough for bare minimum. Meaning, if you are going below 16-bit depth, you can understand the numbers are bonkers, and 16-bit is like bare minimum, like for CDs that was like, we cannot go any lower than this. That's why 16-bit was chosen. So what kind of range it has? It has minus 96 decibel full scale. Now this is a mathematical ratios. Be mindful, no circuit ever works at mathematically perfect point. So below standards, basically, let's say from bottom end, a few of the decibels are just noise. So you're not even able to store any actual audio there. If you did that, it will be just noise. So practical usable is a bit smaller, but it's still more than good enough. It's more than good enough. So 16-bit fixed points is more than good enough. That's how CD audio became to, and that's the first time people started to receive high fidelity music. So more than good enough. That's awesome. Then we have 24-bit. This is where you have wings, so to say. Now you have minus 144 decibel full scale. Mathematically, how much range you have. Now you can easily see that. So that's comfortable order, and that exceeds. Basically, these are mathematical value, but it does exceed the range that your hearing can handle comfortably. But again, be mindful, whenever you are talking about mathematical range, it's clean. When you are talking about real world electronics, it always has noise. Lot of noise on the top end, lot of noise in the bottom end. So there is only a slice that is perfect. So human can touch what we call 130 decibel sound pressure, the actual sound pressure. Now, can our mics handle it? Actually, yes, our mics have reaching this sort of point. And as you must have seen any boom boom channel, they have a very dedicated mic for that. That mic can actually handle it. Of course, it won't be very feature rich at lower frequency, but at high frequency or like high amplitude level, where it's like, I got this. Do not use a sensitive mic, it will go kaboom just by the basically sound pressure. Not even the shock wave, just sound pressure will destroy the membrane. So humans can handle that. So we have reached a point where bass noise, all the algorithms, the bass noise is so low that is like it's almost forgotten. And I'm talking about on a receiving end, not for mastering. Be mindful, these two things are completely separate. Mastering, you want to go as high as you can, but when you're delivering, you have to be practical. 16-bit was more than good enough. And can we drop it lower? Absolutely. With modern algorithm and noise shaping, be mindful, the lower the bit depth, the more quantization noise would be there. So you have to shift the noise into that high frequency zone, so we do not perceive it. So 16-bit is bare minimum. 24-bit is like good, like more than good enough. Like we don't even try to reach 24-bit. And whenever you are talking about like mastering, then we go a bit higher. Now be mindful, whenever we are talking about mastering, we're talking about mastering in a virtual space. You have captured the digital mathematical values. That mathematical values goes into a workspace of your digital DAW, as they say, DWS. And in that space, there is even bigger daddy. That daddy is known as 32-bit float. This puppy. Now this is the only puppy that can truly handle basically the dynamic range, while it can actually allow you to go between 80 decibel to 81 decibel. Like that's decibel jump, it can slice in between them with a resolution of 23 bits. It's surprisingly precise. It's like float. The moment you touch float, the dynamic range becomes bonkers. How bonkers? Above zero, basically these things were normalized to zero. This, because it has a sine bit, this puppy, there is no point of normalizing it. So it goes from 0 up to 700 plus decibel, below 700 decibel plus. Why? Because again, it has a sine bit. One bit is dedicated just to whether it's a positive system or negative system. And then it has exponent. So if you ever seen what is the mass of the earth or mass of the sun, they'll have a number multiplied by a multiplier. That's the same thing here. So you have an exponent and you have a fractional, basically mantissa, and I forgot what they used to call it. I've linked a detailed mathematical video if you want to blow up your brain. Be mindful, do that at your own risk. So now, why do we need this in your digital processing system? Be mindful, even if you're only capturing a 32-bit, as in like 24-bit recording, like your audio recorder is 30, especially in high frequency, there is a serious risk of what we classify as constructive interference, meaning you have two audio streams, especially let's say drummers are doing that. They always reach this point. You have frequencies. As long as they're offset, perfect. But what if one tone reached a point where these two waves reached a point where they're constructively building each up? They will build beyond 24-bit. Because if the signal was mathematically hot, I'm not talking physical sound level, mathematically hot, like full scale level, it was, let's say, recorded at minus 6 dB, which you may want to try. And let's say it was minus 6, 2 minus 6 combined, it will exceed 0 dB. At that point, computer will be like, what the hell? So for that reason, they use this 32-bit float as a background layer. So all your audio is getting mapped to this puppy. This puppy is doing the final crunching, and after this spits out the value whatever you need. You can split it out to 16-bit, split it out to 24-bit, that's up to you. But this is the main crunching part. Nowadays you can receive this 32-bit float recorder. If you have multiple analog to digital converter, now you can reach a point where a microphone can directly capture 130 decibels directly, real sound pressure, and noise would be so low that it would be like, yeah, you are actually getting almost 128 decibels of actual signal. And what does that mean? That simply means we have reached a point where we no longer have to set gain. Be mindful, this can store the data, but it assumes you have multiple analog to digital circuits. One cannot do this. You need multiple, like Zoom has that, Mixfree has that, Tascam also has some of them. Be mindful. And be mindful how complex this part is. Rode has released a new microphone that is like studio grade. It has 4 analog to digital circuit, and each of them are dumping their data. Only then you're going to get perfectly smooth volume at that sort of resolution. If you're complaining about that microphone, there is a very good chance it's about the signature. Be mindful, sound is, I specified, all our ears are different. So it could be one person would be orgasming over the microphone, you would be like, what the hell is this microphone? So it's one of those things that you have to be mindful. So 32-bit, if you have multiple A to D, what we classify as high dynamic range. Unfortunately, there is no technical term for it, so we cannot say this. Many people say, oh, we have 32 dynamic range. Really? Do you have multiple analog digital converter? Only then it actually means anything. If they do not, it does not mean anything. And be mindful, sound pressure and mathematical full scale, they're completely different. They're arbitrary, so to say. So we have to do all the editing is always done in 32-bit float. Now be mindful, even if your software does not allow you to import a 32-bit float file, does not mean it's not doing that 32-bit float. It's just maybe not designed to digest, quote unquote, a file. It was like, hey, I was designed to work on this system. So this is how we handle the bit depth. Now bit depth also has the same rule. For giving to audience, 24-bit is more than enough. To processing and do the crunching, you need 32-bit float. Be mindful, all that, even Audacity does this. So be mindful, anybody's like, oh, you don't need 32-bit, it's already there. It's always there. It has to be there. Capturing it again, now you have a microphone that can have multiple parallel analog to digital converter. Now you can absorb the data into this puppy. This puppy can give you really high quality signal to noise ratio, and that allows you to actually capture a full range of the microphone. Why would you fight it? It's like, I want to shoot in JPEG. No, you want to shoot in RAW, deliver in JPEG. Clear these two things apart. I have seen way too many basically technicians who are actual expert, but they are like, what the hell are you talking about? It's like, there is a reason for that. Like, these two things are separate. You always want your master to be as rich as possible, then you dump it down. Then you quantize it down to lower bit depth. If you have a good amount of richness in the sound, quantization will happen very efficiently. If not, good luck. So this was the bits part. I have linked a very detailed video down below. You should check it out. So this was my presentation on basically sample rates and bit depth. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.